Good afternoon, everyone. Here's another Kent seminar. I think starting with Dr. Taylor. We're starting. So we can have really good speakers in the next couple of months. We're starting with Dr. Taylor. He's a professor at Iowa State University and the director of the Concrete Pavement Technology Center. I'm really pleased to have him here today to talk about one of the trend topics in the concrete pavements, performance-based concrete mixtures. I don't know too much about this, but I'm really eager to learn today from his presentation. So, he's again the director of the National Concrete Pavement Technology at Iowa State University, and then let's give him a warm round of applause to get him started with his presentation.
Well, thank you very much. It's a real privilege to have been invited to come and do this. So my thanks to Hassan and Imad for this opportunity to come and talk to you. The title he asked me to talk about was specifications. I've got way too many slides for the time slot. And I also want you to ask me questions. Let's make this a discussion. I can be really, really boring. So if you want to ask questions, discuss, let's argue a little bit. It should be a little bit more entertaining. My first few slides, I'm going to talk a little bit about the center that I work for, what we do, and why we do it. We like to see ourselves at the nexus, the joint between industry, academia, and agencies. So I'm not a pure academic researcher type guy. What I do is that as we say up here, the purpose of the center is to unite agencies, industry, and researchers to get good concrete practice on the ground. We don't do advocacy. So I'm not trying to compare concrete with that other bad stuff. But I am trying to make sure that if anybody is working with concrete, they're going to do a really good job with it. What is the latest technology? What's the good way of doing things? How do we get it in place? How do we do that? We talk to smart people like Jeff and learn things. We take the information that the researchers around the country are doing. We write books, we prepare presentations, we travel a lot, we do a lot of workshops and that sort of stuff. I'm just coming off a 3-week stretch. I don't think I've been home more than about 2 nights in the last 3 weeks. So if I fall asleep halfway through the presentation, just give me some more caffeine and we'll be all right. We write books. We write anything from a 400-page manual to 4 or 5-page tech briefs, those sort of things, aimed at practitioners, trying to make sure that the people that are actually doing the work know how to do their jobs properly. Because frankly, what we're teaching our undergrad students isn't great. And we need to go back and help support the young graduates, the young people that are out there in their jobs, give them the tools and the technologies that they really need. We also help a little bit with problem solving. We try not to compete with the consultants, but if something really weird and strange comes up, we'll engage. The one example is Missouri has recently had a couple of cases of alkali carbonate reaction, and very few people know about it. So it's been an opportunity for us to go in there, work with the agency, the contractors, and the material suppliers and figure out what on earth is going on. What is this beast called ACR? What does it look like? And who do we blame? We also get involved in things like this, getting in front of audiences and talking about good practice. Hassan spent the morning trying to persuade me to join ASCE. That's the one professional association I'm not a member of yet.
Did I convince you?
I think you have, yeah. We're a pretty small group. I've got 6 professional staff, 5 or 6 professional staff, and a few support staff. And the rest of the work that we do is using consultants. And Jeff is one of those people. When we need expertise in structural design of pavements, stuff to do with fibers, Jeff's the guy we call. Send him out to go and do a workshop for us. Send him out to write an app or design stuff for us. So we've got access to a lot of the real smart people around the country. And that really works for us. We've got people from coast to coast in all aspects of concrete pavement technology. Who do we talk to? Mainly states. So the agencies. We're trying to solve their problems. But we're also engaged with industry. and they come to us also with problems they have, education they need. So again, research is a part of my life. I'm appointed as associate research professor. So my annual performance review is how many papers and how many PhDs. And every year I fail, but that's okay because my sponsors like what I'm doing. So tough. But what we're doing is getting good technology on the ground. How we pay for all of this, about 20% of our budget comes from sponsorship. The trade associations and the Iowa DOT give us money, which allows me to spend time doing things like this. Spend time at ASTM, ASCE in the future, TRB, going to those sort of meetings. Working with FHWA. We also drive, one item up here is the so-called CP roadmap. This is a thing we're trying to keep alive, which is to try and coordinate research so that we're not getting $30,000 being spent in Illinois and another $30,000 being spent in Iowa on the same topic. Let's put those two 30s together, make it 60. Now we can actually do some work and get one good project out of it, or at least coordinate with each other. Realize, I had an occasion last week, discovered there was a professor in Wisconsin working on exactly the same topic that one of my students is working on. So next week, we've got a phone call, we get the two students together, and hopefully we're going to get a single paper out of it. We're going to write a specification for AASHTO out of combining the two sets of work, which were very similar. Trying to coordinate and leverage research. The remaining 80% of the money that our center gets is from competitively won contracts. All right, that's the boring part. Let's get on to what are we doing? So let's think a little bit about what are we trying to achieve? Start with this concept of what is the perfect pavement? Well, it's something that's going to last forever, doesn't impact the environment, is great for the traveling public. And the term that my children use when we're driving around is they really want it to be smooth and creamy, whatever that means. That's a test method that we need. All right, how do we achieve that? We make concrete, of course. But how do we make the concrete sustainable, safe, and smooth? What's really interesting is that I came across this photograph. This is one of the oldest pavements in Iowa. It's more than 100 years old. And it suddenly struck me how similar it looked to the image on the right, which is the yellow brick road to the land of Oz. The image on the left is actually in a graveyard. So land of Oz, yeah, okay, we won't go there too far. What's the perfect material for a pavement? It's got to be cost effective, it's got to be easy to build with, blah, blah, blah. You can read the bullets just as well as I can. And meeting some of the challenges. How do we get traffic onto a concrete pavement quickly without beating it up? Those are the sort of things that we need to start thinking about. How do we make a pavement weatherproof, resilient? So when the flood comes, will the pavement still be there when it drains away? All right, to do that, we need a good specification. What's the perfect specification? Well, the perfect spec is you build it. If it's still there in 40 years, I'll pay for it. I mean, that's the way we do a lot of stuff. You buy it. Take the cell phone. I bought it. I paid cash for it. If it stops working, what am I going to do? Take it straight back to the store, slap it on the counter, and demand another one. Right? A little tricky to do with a pavement. You can't pick them up quite so easily. But ideally, that's what we'd like to be able to do. Reality, we can't. So instead, what we have to do is to do a bunch of testing. We put the concrete down and we measure it, and then ask the question, how does the result of that test tie to how long that concrete is going to last? And the answer is, it depends. And where we need to make progress, and are starting to do so now, is tying together the test methods to the actual things that go wrong. You look at most concrete pavement specifications right now, what do they want us to measure? Slump strength and ebb. So my trick question to you is, So how does slump tell us anything about how long the concrete's going to last? Anybody want to take that one on? Yeah, you're all afraid. All right. Slump doesn't tell us anything about how wet, except how wet the concrete is. Now, 40 years ago, when water was the only lever we could pull to change the properties of the mixture, knowing slump was kind of useful. Nowadays, when we're packing it full of chemicals, slump is useful from the point of view of telling us that this truck looks the same as that truck, but other than that, is useless. Strength? Yeah, no. Structural engineers get all excited about strength. They live and die by it. They can't sleep at night until they know the 28-day number. For pavements, nah. Every time I do this, I ask, when did you last see a concrete pavement fail because it wasn't strong enough? I've had the answer yes, twice. Both times it was somebody sitting in the front row. So when did you last see a because we pay so much attention to strength, we've got it down. And the problem is that it's leading to some unintended consequences. Because by jacking up strength, we may be compromising shrinkage, permeability, heat, cost, sustainability. Iowa does not specify strength. It doesn't even measure it. So when I travel to some places and say, we don't measure strength, you can see people, their hair is curling, they're panicking. Doesn't matter. Because we're measuring the properties that really matter. And so the question is, what are those properties? Also had a discussion the other day with a few people about what's the perfect specification and what are the challenges. And one of them is this, there's a feeling of just get out of the way, let the good contractors go and do the work and stop interfering with their lives. There's a certain validity to this. Okay, again, my model is the cell phone. The way my daughter chooses her cell phone, does it have a picture of a fruit on the back? Right? As long as it has that, she's happy. All right. Now that would work in a pavement if you knew the contractor, trusted them, and they'd been around a while. The problem being is that in a low bid situation, the lowest bid may not be the best because somebody's cutting corners unless the specification prevents those corners from being cut. So while Chelik has a lot of weight, I'm not sure he's quite right in a low bid world. Then there's Minnesota, who go the other extreme. They're the control freaks. Admit it, you're all engineers, you're all control freaks to some extent. And Maria's position is pretty valid. Her concern is that you're going to get some contractor who's never played before, going to bid low, win the contract, and then realize, uh-oh, I don't know what I'm doing. I'm not going to make money out of this. They're going to cut corners. Then you've got a real problem. So maybe we need to be doing this idea of trust but verify. You know, we'll write a spec that says, okay, we believe you can do it, but yeah, we're going to make sure that you can. We've got to find the middle point between these two pendulum extremes. Why bother rewriting our specs? Aren't they good enough? We've been building concrete pavements for more than 100 years. Well, yes and no. Life is changing on us. Currently, most specs, as I said, focused on strength. This core comes from a pavement in the Midwest where the local agency spent several $100,000 with a university with the local materials. The materials they have are not pretty. The aggregates are ugly. The sand isn't sand, it's just fine rock. It's not even crushed sand, it's chip. Okay? So they got really ugly materials. They spent a fortune, did a whole bunch of work, came up with a mixed proportioning system in order to optimize strength. They were getting it within 50 psi, really fine-tuning this thing, every ounce of every item to get strength. And the problem is that most of the pavements in that area look like this. They tear. The workability is ugly. The permeability is ugly. It's strong, big whoop. The concrete pavements are failing prematurely because you're measuring the wrong things. Struggling to get durability. Wrestling with unintended consequences. Okay, that image You know, the law in the town where I did my PhD, Cape Town, they haven't had rain in 5 years. They're desperately short of water. They're on water rationing. And one of the laws is that you're not allowed to water your garden using a hose pipe. So if you look closely at that image, you'll see that the gentleman is being very compliant with the law. He's not watering the garden with a hose pipe. He's watering the garden with a watering can attached to a hose pipe. Okay? Strictly his compliance with the specification. Is he doing a good job? Is he meeting the intent? No. And those are the problems that we have to try and deal with. All right, on the left-hand side, design and control of concrete mixtures, the Bible of concrete in the USA, the 1958 edition, 60 pages. The 1916 edition, 640 pages. Now, it doesn't mean that concrete is a whole lot different. It just means that a bunch of professors have learned a whole bunch on the way past. We can write more about this stuff. But life is more complicated. Some of the things we're doing, we're putting more stuff in our concrete, more ingredients. We're putting supplementary materials in. We're putting 2 or 3 admixtures in. You know, when I grew up, long, long ago, we had rock, we had sand, we had water and cement. That was it. 4 ingredients. Now we're playing with 7 or 8. How do you juggle those to get the performance that you want? We're also changing our timeline. Instead of trying to open it after several weeks, we're opening it after several days at best, maybe several hours if we're in a high lane rental facility. How do we do curing? Used to be weeks. Now it's days. What is the environment we're exposing it to? Sodium chloride was the only salt we used. Now we're doing all sorts of other stuff. And that stuff eats concrete. We've got to make the concrete better to resist the environment we're trying to hit. 40 years ago, design life of a pavement was 20 years. California now is looking for 100 years. Makes our lives a little more complicated. The other part of it is just a changing knowledge base. Not long ago, the repository for practical knowledge was with the Departments of Transportation. Those guys are retiring, getting into management, and are not being replaced. Instead, the services that they provided are now being sent out to consultants. And how do consultants get paid? By the hour. And I've had more than one consultant tell me, I don't have time to think. That's terrifying. So we've got to write our rules to make it simple, but idiot-proof. And that's a real challenge. The other principle is that if we can reduce the risk of early failure, our projected lifetime gets longer. And the fundamental laws, you know, what I learned in my woodworking shop long, long ago, measure twice, cut once. You save time and effort. I won't go into more detail of that one. So we set out with a vision about 5 years ago with FHWA, myself, and ACPA, and said, what does make concrete good? It's not slump and strength and air. Once we've figured out what it is that makes concrete good, let's find the tests that measure those things. Then we can set the limits. Then we can write a specification. And the challenging part of this is this question. I've been at a meeting the last 2 days looking at a new specification, and a lot of the discussion was coming out of the states saying, and the contractors, because the contractors are terrified of concrete that is good failing because of a bad test result. And at the same time, the agencies are equally terrified of bad concrete being accepted because of a bad test result. And that comes down to, what are we doing with our tests? How predictable are they? How reliable are they? All right. I was in your lab a little earlier. I noticed some compression cylinders. I wouldn't accept data coming out of those numbers. They look really bad. So, you know, you're getting false numbers out of a bad test. We have to find a better way to do that. All right. The other thing that we're seeking to do is to help the contractors. If we change the rules, we have to provide guidance on how do you meet those rules? How do you make a mix that's going to meet the requirements we're looking for? Did a session in another state in the West back in December. And we invited all of the DOT staff to get into a corner and talk among themselves in little groups, and then come back and give us some feedback. And they listened to us drone on about performance specifications for a while, and they all came back and said, the reality is we can't do it. And the reasons they gave, we've done it this way for the last 40 years, we can't possibly change. You'll notice my rather clever activities putting a slump cone underneath Tevye there. All right, politics. The governor says we can't change. Changing workforce. Balancing risk, this idea of if something goes wrong, who takes the blame for it? And what we also found in that meeting was that the fundamental understanding of the material we were dealing with was pretty thin. It was terrifying. I made a comment that the property that controls concrete performance predominantly is water-cement ratio. And that adding cement to a mixture without changing the water-cement ratio did not affect performance other than workability. And these guys were all in hysterics because they don't understand the mixture at a fundamental level. We also have to understand the limitations of the test. Where is it valid? How easy is it to skew the test and make it get the result you want? Anyway, the way we set about this is we gathered together a group of experts from around the country, agency, academia, and consultants, and said to them, what makes concrete good? And I'll get to that in a couple of minutes. We took that information and we prepared a document. It's not a specification, more a guide of practice. PP84 was published by AASHTO in March of last year. It's deemed to satisfy. We haven't put any sort of statistical modeling on it yet. We don't have the data. It is provisional. It means we can go back and change the rules as we learn things. So that document is out there. And we're starting the process to figure out, can we actually implement this in real-life concrete? There is a perception whenever I meet with industry people, they think that the whole idea of what we're trying to do is just make their lives miserable. Okay, the joke behind the image is that the cruising speed for a cheetah is about 3 times the posted speed limit right there. But the reality is that we're actually trying to make your lives better. We're actually trying to reduce the testing burden. We're trying to make the tests more reliable. And we're trying to provide the agencies with better concrete at the end of the day. So the properties that this group agreed on are these. 6 different topics. Transport properties, the ability to keep water out of the concrete. The stability of the aggregates, strength, cold weather resistance, shrinkage, and workability. Let's look at each one of these in turn. I remember my first transportation lecture in 1979. The professor, old German guy, stood up and said, if you only learn one thing out of this class in the next year, it is this. You've got to keep water away from your pavement. And we're still struggling with that. Okay, water that penetrates concrete will carry nasty chemicals with it, can set up freeze-thaw. All of the premature materials-related distress related to concrete pavements, there's water involved in it. Keep the water out of the system. How do we measure that? That has been the challenge. Up until now, the rapid chloride test is a misnomer. It's not rapid. It doesn't measure chloride movement. It doesn't measure permeability. And some would question whether or not it's actually a test. It was a challenge. And again, the issue with the rapid chloride test, the error on that thing is huge. If you specify 1,000 coulomb and you get 1,500, is that an acceptable result or not? Well, 1,500 is bigger than 1,000, obviously not. But wait, the error on the test is 500 coulombs. So it means that 1,500 may actually be acceptable. We've got to find better tests. All right, so the way we wrote this into the spec, we offered 3 different alternatives. One was based on a performance approach, water-cement ratio. The other was based on a prescriptive approach. We're using formation factor or resistivity. We've said very explicitly, measured Measure just one of these. Don't ask for all of them. That's stupid. Pick one. All right, and it's up to the agency to choose which one. And we will help each agency depending on their sophistication, depending on what lab facilities they have. Personally, I would bias towards the performance specs every time. The other thing that we have added in here is that you don't need to measure every property with every load of concrete. There's a time to measure at the beginning with mixture qualification. In the lab, get to know your mix. Is it going to get there? Then when you're on the construction site, do we need to use these tests for acceptance? And look at that column on this table as we go through the different versions of it all the way through. Sometimes it says yes. All of them say yes on qualification. It only says yes on a few of the acceptance tests. The philosophy being is that if I know that this mixture is going to work, then the stuff that you deliver tomorrow, if it looks the same as the stuff that I liked today, we should be in good shape. The real trick is getting that confirmation that it does actually look the same. Formation factor, fairly complex modeling game. Actually, testing is pretty easy. The resistivity test is pretty simple. It's almost idiot-proof. It's also non-destructive. So you can test the same sample at 3, 7, 28, and 56 days. Get to know the shape of the curve. So that means for this mixture, I can test it at 3 days. If it's the same as the 3-day result I got in the lab, we're in good shape. And again, we can keep measuring it over time. And so again, the table has provided some guidelines on how to calculate it, how to get to the formation factor, which is the fundamental property we're really looking for. Aggregate stability. We avoided that one. Very complex stuff. Some very good work coming out of Texas and out of Canada with alkali silica reaction. We figured we're not going to argue with that. We just referred to the ASHTO document R80, which provides the guidance on how to address ASR and ACR. For decracking, we referred to the freeze-thaw test. Personally, or what we said was, use what your own state is doing. I don't think it's too much of an issue here in Illinois, maybe in the northwest. But, in Iowa, it's a real issue. But the Iowa DOT has a very good handle of what aggregates are bad and which aggregates are not. So we've defaulted to, you guys know what you're doing, carry on doing it. All right. We'll skip over that to save time. We were tempted to take strength out. But then we thought about it and decided, no, we still need some strength. Why? Because we still put heavy trucks onto a brittle system sitting on a flexible foundation. We need some strength. The real trick is not to overspecify it, and better still, don't pay bonus on it. So whether or not you go with flexural or compressive, I don't really care. Whichever works for the agency that you're working with, carry on. We're familiar with this activity. It's not new. We don't have to go into a lot of detail. The freeze-thaw side is probably the most challenging one to address. Most of you are probably familiar with freezing and thawing, this action of water getting into concrete, freezing, expanding, and causing mechanical damage. The relatively new one in town is the formation of calcium oxychloride. Putting mag chloride or calcium chloride de-icing salts on the pavement. Those chlorides combine with the calcium hydroxide from the hydration and form this wonderful compound called calcium oxychloride that's 3 times more expansive than water freezing to ice. It causes a lot of damage. It's also very difficult to find after the effect because it's unstable. It only forms and is stable at relatively cool temperatures. A day like today, all right, the snow's pretty well gone. It's raining and not snowing. It's in the 40s and 50s. We're starting to warm up. I'm not wearing my down coat. Life is getting good. Maybe I'll get on my motorcycle on Saturday. Life is going to be wonderful. But the concrete outside is quietly dying because it's at this temperature. the oxychloride is forming, expanding, causing damage, and is stable. Come summer, when it warms up, we pull a core and take it into the lab, and it's 72 degrees. The oxychloride decomposes and disappears. So doing forensics on it is really difficult. So that's why we set up the table in two different blocks. The red block covers the freeze-thaw. Again, prescriptive, air content, or water-cement ratio. The performance, super air meter, time to critical saturation. Couple of other slightly more rigorous test methods. On the green side, which is the oxychloride concern, prescriptive, the current thinking is that if you can put 35% of any supplementary cementing material into the mixture, you'll prevent oxychloride formation. Now, the challenge is that 35% fly ash that you're trying to put down in concrete in November scares me a lot. The risk of cracking is huge. We've got to work out how to get around that. But that's the default number. We can measure the chemistry of the system and figure it out. We can put sealants on it, or we can do the testing using low temperature differential scanning calorimetry and look at whether or not it's going to form in a chemical test. All right, so again, I don't need to go into a lot of detail. Freezing and thawing is all about the air voids and the fact that they delay saturation. They prevent the system from getting full of water that's going to expand. How much air do you need? Enough. I'm still holding to, I want 5% air behind the paver, and I think that's new language. Many specifications only measure air in front of the paver. Our experience is that with some systems, the air void system is not stable, depending on the chemistry of the admixtures. The combination of some water reducers with some air entraining admixtures give us systems that are not stable. So again, know the materials you're working with. How much air loss are you getting through the paving machine? Keep an eye, again, for the agencies, keep an eye on variability. If it starts drifting upwards and hits an action limit, take action. Don't just say, oh, look, it's going up. All right? You can see it before it gets to be really bad. All right? Then there's the super air meter. This is a device that comes closer to actually measuring the effectiveness of how small and how frequent the bubbles are, how close they are to each other. The catch with this test is that the maintenance of the machine is important. If it leaks, you are doomed, and the operators have to be thoroughly trained. You're probably looking at 2 days of training to get operators that actually know what they're doing on this test method. The chart here, the blue dots are data points collected in my lab over a period of 3 months. And I got concerned because the horizontal axis is data from one machine, vertical axis is data from the same mix on a different machine. And you can see that the correlation is pretty poor. So we called the manufacturer of the SAM meter up to our lab. He spent a day refurbishing the machine, fixing all of the seals. He spent a day teaching all the students and staff how to run it and on water, and then another day teaching them how to run it on concrete. Since then, we've been collecting data with the red dots. It's a lot better. Still not perfect, but a lot better. What I learned from that is that training and maintenance are absolutely critical if we're going to be using this toy. All right, the oxychloride, again, is a chemical reaction. I've talked about this. We measure the potential risk using the LTDSC machine. What we're concerned about is that peak. The bigger the peak, the more of a problem we have. We have this toy. We're learning how to use it. If anybody wants to play around with some cements or cementitious systems, we'll be happy to talk to you to help advance the state of knowledge with it. We also been running samples on putting different sealants onto concrete and seeing how much they expand. Now the red line is the control. That's the sample without any sealant applied to it. the black lines are various different products of all sorts of chemistries that we've been playing with, and I've carefully not labeled them, particularly the one at the top that actually made the system worse. We've also been running an interesting little test. The photograph on the bottom right, you may or may not be able to see it, but we're using low-angled light, and you can see round about here, there's a shadow. It's because the paste has expanded and risen above the surface of the concrete, of the aggregate. And so we monitor the size of that step over time with samples exposed to 40-degree mag chloride. And that's what that chart is, time versus expansion. And it seems to be working pretty well. It correlates with the LTDSC pretty well. All right. The other property we're looking for is shrinkage. Why? Because we're worried about random cracking on the right, warping on the left. How do we measure it? In this case, in the table, we've given a lot of alternatives. Prescriptive is how much paste do you have in the mixture. The less paste you have, that's the part that's moving. So if you've got less of it, your total shrinkage is going to be reduced. Otherwise, we can go with the standard C157 test, a ring test, or different versions of the dual ring test. I quite like the standard ring test. It gives us information. It starts collecting information immediately after casting. The C157 test only starts after 24 to 48 hours. You lose a lot of information in that time. The challenge with the standard ring test is the variability is pretty high. This would be a test that you don't run every day. You do it in the pre-qualification stage. All right, then we get to workability. For years, I've traveled the country and spoken to people and said, why does the agency specify slump? Because you can. Does it tell you anything? Does it provide any quality assurance? Not really. It tells us something about uniformity, but really the workability should be the domain of the contractor. Because if he's using a big fat machine with lots of vibrators, he can deal with a far stiffer machine than a mixture required for a thin, lightweight, or hand placement. Let the contractor choose the workability for his own device. But what we found as we talked about it is if the workability is wrong, the contractor won't stop and go away and fix it. He'll just beat through it. And the photo on the left is the classic example of a pavement where the mixture was far too bony. It was an ugly mixture. It segregated, it was hard to put down, it didn't get a good surface on it. And so the contractor was running with his vibrators at full speed, 12,000 vibrations per minute. He was running this thing hard. And in the end, what he ended up doing was segregating the mortar from the rock. So above each of the tracks where the vibrators were running, there's only mortar, no coarse aggregate. He also beat all the air out of that system. And so now, 10 years later, that system is showing fairly clear signs of freeze thaw damage. 18 inches apart, precisely where the vibrators were running. Unfortunately, that piece of pavement's about 20 miles away from where I live. If it's too wet, we have edge slump. So we want to be somewhere in between those two extremes. The two tests we have that help assess this are the box test and the V. Kelly test. I'll talk about those in a bit. This stuff works. This is two photographs I got from a contractor in Pennsylvania last week. This guy's been bugging me. I was providing him some help with mixed proportioning all of last winter. Last week he emailed me and said, the photo on the left, that's what we built last year. It's full of bug holes, poorly vibrated, poorly consolidated. The one on the right, using the mixture that you helped us design, is beautiful. I'm going to take all the credit in the world for that. That all of a sudden now we have concrete that's going to last longer because it's got fewer bug holes in it. The water can't get into it. The test we developed is called a V. Kelly. It's a hemisphere that weighs about 30 pounds We've bolted a vibrator onto it, and on the horizontal axis, we've got square root of time. And on the vertical axis, we've got the depth that this thing sinks when the vibrator is running. And what we're really interested in is the slope. And something with a flat slope is not responsive to vibration. Something with a steep slope is very responsive to vibration. And some of you are working on a similar sort of concept with Professor Lang. So we're all trying to do the same basic idea. This thing works for mixtures up to about a 3-inch slump. What we did is we fooled around with 3 different mixtures, 3 different aggregate gradations. Same materials, just different gradations. Different combinations of coarse, fine, and intermediate. Same binder content, same water-cement ratio. This curve at the bottom was an ugly gradation. This is a mixture constrained to fit as close as we could onto a power 45 curve. This one is constrained to be as close as we can inside the so-called tarantula curve. And what it's telling us is that for the same cement content, I can get, to get the same workability, I either have to be at 7 sacks of cement, 5.5 sacks of cement, or 5 sacks of cement. Now, taking a sack of cement out of a concrete mixture is a pretty big deal in terms of cost, shrinkage, heat, and sustainability. It's all a win, just by fooling with the gradation. It's worth doing. So the box test is a cubic box, foot in each direction. You fill it up with concrete, vibrate it for 6 seconds, strip the forms off and look at the surface. If it's got full of holes, that's bad. If it's nice and smooth, that's pretty. We also look at the curvature on this edge. If it stands up straight, that's good. If its edge slumps, that's bad. A little subjective. So either one of those tests work. We're also saying the agency, the contractor, needs to pay more attention to the quality control system. There are a lot of tests which are useful information that help you understand that the mixture is working well. It's going to get to the specified numbers that we need. But the agency shouldn't be worrying about them. Things like unit weight, calorimetry of the raw materials coming in, maturity. Those are the contractor's toys. He should be using them. So we've written into the spec guidance on these are the things you should be paying attention to and how do you do it. I'm not going to go into detail of all of those. So, fundamentally, we think we've got a pretty good framework in place. It's early days yet. We had a meeting for the last 2 days in Chicago. 30 people from agency, industry, and a couple of academics talking about how do we get this into real practice? It's a big uphill struggle. We've got a pooled fund running. We're going to be out there. Illinois is part of the group. James Kristolovich was at the meeting with us, and it was great to have him there. We're going to be pitching up on a construction site with a little trailer with some of these toys in it to see how you're doing at the moment. How can we help you make a better mix so that it complies with what we're recommending? So that sometime in the future, we can start looking at pilot tests using the basics of the specification approach. All right, I didn't load my final slide onto my flash drive, obviously, but some thoughts on what other tests do we need to make this system keep working better. Some of the stuff you're already playing with. How does vibration affect both workability and the air void system? I think there's still some opportunities for us to understand that better. The effects of putting an interlayer of geotextile underneath an overlay. It's a whole lot easier than putting asphalt down. Sorry, Imad, but that's the way it is. But what sort of geotextile should we use? How thick should it be? What does it do to deformations and movements? How stable is it? What does it do to drainage? We don't understand that too well. We've built several pavements, and they're doing pretty well, but the fundamentals behind why is still up for grabs. And I got a whole bunch of other ideas on, there's still quite a lot of research needed in our materials area. So, the center that I work for, yes, I do a little bit of research. My fundamental goal, though, is to get the work done. Doesn't have to be done by me. You guys got a fantastic set of brains in the room. Let's go and do some good work and get some of this stuff into practice. With that, I will stop and invite questions and discussion.
Lots of time for questions.
Yeah.
Thank you for the presentation. It was a really nice presentation. So, as far as I know, generally payment engineers are finding out payment service life in the payment design process when they put the structure inputs with the thicknesses, all this for design. Most of those payment design procedures are not really including each level inputs.
Correct.
Most of the inputs that you mentioned, and why the people are focusing on the strength, because one of the most significant variables in the design process. So I was just wondering if, are you planning to recommend any changes to existing payment design guidelines, or come up with a modified one, or what is the way between mixture and the...
Yeah, that's a very good question. MEPDG and the design models, the structural design models, are completely silent about materials aspects. They assume it's going to last for however long you're wanting it to last. And so, yeah, they just assume it's going to work and we're all good. The problem then becomes mine to say, well, how do I make sure that I can deliver a mixture that's going to last 40 years under the environment? I'm not sure that I want to, I don't know, Jeff, maybe we need to argue with this about, but in a way I think it's probably good for us to keep these two issues a little separate. But I think it needs to be considered that if you are looking for a 40-year life, you can go and run all the models and say, all right, if it's this thick with this joint spacing with this many dowels in it and these sort of edge support, it's going to last. Then on a separate conversation, you come and talk to the materials geeks and say, all right, it's Illinois. We get 30 inches of snow a year. That we get 40, 50 freeze thaw cycles a year. We're using magnesium chloride. How do we make the concrete last the same period of time? It gives me a chance to come back to one of the slides that I skipped past. We recently completed a little research project with Iowa DOT. Iowa has something like 2,000 miles of concrete overlays in place, some of them up to 40 years old. Data on those 8 pavements is readily available from the DOT records, from industry records, and from the institute that I work for also collects performance records. So we combine these 3 databases and try to make sense of trying to draw performance curves, and that's what this figure is. And what really struck me, my student came to me the first time he put this set of data. Now this is for a given set, a given thickness, and a given joint spacing. And he was pretty concerned that there were clearly 2 different data sets. There's the ones that I've marked in orange, and the different set which I've marked in blue. Now the choice of color here is pretty arbitrary. But to me, it was pretty clear that we had 2 different sets. And the student was all in a panic about, why has this happened? Well, it's actually pretty simple. The orange ones are the ones that are performing like we would want, like MEPDG is assuming. There's a bit of scatter, but they're all pretty much in the same space. We can draw a line through it, and we can model how long it's going to last. Then you got the ones in blue, which are the ones that go, uh-oh, something went wrong. So then we went out to all of those ones in blue to see, well, what went wrong? What was the cause of this premature failure? And it was pretty mixed. Some of them weren't even concrete. They were asphalt. It was just bum data. A couple of them seemed to be design issues. Is that, since they were built, somebody built a factory next to it, and the traffic loading has quadrupled. Several of them were, air void system freeze thaw related. So it was all the things that come out to bite us with ordinary pavement construction. There was nothing about the overlays. But what I really took away from this is that if I was drawing a performance curve for this data set, I'd have to take all of the data. I can't ignore the ones I don't like, the blue ones. So I'd have to draw the gray line, which tells me on average I'm getting 25 years out of my overlays. But then I'm an optimist. If everybody listens to me and does what I says and builds the pavement like I told them without making any mistakes, we're not going to have any of the blue ones. We'll only have the orange ones. Then we get this line, we get 45 years. 20 extra years at no extra cost. And all the DOT people are going, yes! All right? If we reduce our mistakes, we extend life. So yeah, it's a good point though. Being aware that the structural design models do not address materials-related distress is a loud message. Not everybody gets. Sorry, that was a long rant.
Thank you.
That's such a good presentation, I guess. That's why
I'm scared of this.
they're scared, huh?
Or they didn't understand my accent and they're all mad. Yeah.
Thank you for the presentation. So I have a question regarding how can we connect the research with the specification and further to the industry. So we do a lot of work in the university and in the lab, and we use some new method for large chance that the results are good and more insightful than the current method, but it's typically very difficult to implement those methods into the industry or write it into the like ASTM specifications. So there should be something that we can improve from the perspective of a researcher. Do you have any suggestions for us?
Come talk to me. And I'm not joking. That's precisely what the primary role of my center is about. It's less about, you'll notice the test methods that I've discussed here, only one of them is mine. All of the others have come from other faculty or other researchers around the country. So part of my message and one of the joys about being able to do a presentation like this is that if you've got a great idea and you can show me the publications to show that it works, yeah, I will help you get visibility. I will help you get it, if we need to get it into AASHTO. ASTM, yeah, no, that, well, yeah. Ideally one day when you're old and gray, it might happen. But AASHTO, we've got a conduit. We can make things happen in AASHTO pretty quickly. So again, the guidance books that we help write are based on what we're learning from you. So yes, come and talk to me. If you've got something great, we'll include it in the materials that we're using as we travel around the country and teach. Hassan.
Your AASHTO spec looks rather unorthodox because you have really multiple options for each parameter.
Yes.
Usually what we do, the way we do our business asphalt, on the back side is my test or highway.
Right.
So, well, what is your vision? Are you visioning that this spec is out there that will be used? Maybe there's a couple of other tests that will just be not good, and then they will be eliminated, and you'll be more prescriptive specifications in the future.
Probably less prescriptive and more performance. The reason we went this route, the first version that I wrote of that document said only performance. So, for freeze thaw, calcium oxychloride. For shrinkage, do the ring test. The problem being is that a pure performance spec, you're entirely dependent on the quality of the test, and some of these are unproven. And that's the challenge we have over the next couple of years, is demonstrating the variability of the test, how much training we have to do. There's also the practicality. Look at the shrinkage test. The ring test, depending on what version you do, takes a couple of weeks. It's got a fairly high variability. While for me to go and look at a batch sheet that says 28% paste content, I'm done. And that's why and we also acknowledge in the Midwest, where we build a lot of concrete, we have a community that's pretty sophisticated. I can gather materials engineers from around this area who know what they're doing. So I can come to them with an exotic test and say, try it out. They'll probably do a good job, get used to it, be able to adopt it. If I go to Alabama, that last built a concrete pavement in 1950, and say to them, here's a fancy new test, ain't going to happen. So that's why in the end, as we worked with the committee and negotiated with the other, we went to this optional route of saying, for the people that know what they're doing, go and do the performance stuff. For the people that are new at this game, dabbing their feet back in the water of playing with concrete for the first time, let's start with the prescriptive. It'll be a little easier for you to do it. Personally, I would like to see it biased towards the performance further on. Now, one of the questions is, do we have the right test? Is there a better test for these properties? I think the list of properties is pretty well closed out. But are there better ways of measuring each one of these things? Maybe. I heard 2 days ago, Tyler Lay gave a presentation. He's figured out a way to measure water-cement ratio not using the microwave. Says it takes him 30 minutes. If it works, that's a home run right there. So, we'll never be pure performance because it's in many ways just impractical. But finding the right balance in that hybrid will be a local issue. So what we do here in Illinois will be different from what we do in Kansas. And again, something we do need to make clear, when you're in the table, it very clearly says, when you're writing your specification, the circle on the left, pick one. Because, when I was working in consulting, the number of times I got an exercise of, please help us develop some mixed proportions. By the way, the cement content is fixed, the water-cement ratio is fixed, and the slump is fixed. So what could I change? Nothing. So I wouldn't change anything. I'd send it back to them, charge them $5,000, and we're all good. Keep going. Have I finished the discussion? Yeah.
Thank you. For this table, for example, you said choose one, but in theory, if you get result, for example, in the water-cement ratio only, and you are always in the range that you're specifying, in theory, you're going to be in the range specified for the other test at the same time?
Kind of, sort of, maybe. The question is, for those online, is that are these lines or the values that we're calling for equivalent? And the answer is, I'm not sure. We like to think so, and that's one of the big concerns we're hearing out of industry. I think they may be, in which case it may be easier just to default for water-cement ratio for everything and go home. But from a uniformity point of view, I think I'd still be happier with getting a formation factor reading. Again, that test is quick, dirty, cheap, and easy. So that one I would be quite happy to say, run with it. It's something that we've still got to figure out.
All right, I think we're done with our representation. So Dr. Taylor will stay in the room if you're interested in talking with him. He's going to be staying just for another half an hour. So let's just thank him with a warm round of applause.
Again, thanks for the opportunity.